Next presentation is this Spotify music recommendation system. Okay, perfect. Roshani,
Hi, can you see my presentation?
yes, we can hear you and see your presentation.
Yes, okay, great. So this is my presentation. Hi, I'm Roshni, and my project is on a Spotify music recommendation system using quantum machine learning. Before I get into kind of like everything that's over here. I just want you to, there's a GitHub link right here to my project. If you want to look more in depth into it, or if you want to kind of look at the code as I'm speaking, then you can scan this link right here and it'll guide you to my entire project and the entire description of it. So, getting right into the introduction of this. So, for anybody who doesn't know, Spotify is a music streaming application. So, you can listen to music on that. And one of the cool things about Spotify is that it actually recommends music to you. Depending on, obviously, the more music you listen to, the better these recommendations get. So, what I've tried to do is I've tried to replicate that recommendation algorithm using, a user's historical kind of like what they've listened to in the past and what they like and what they don't like to be able to recommend new music to them that they would like. And I've used quantum machine learning for this. So that is the objective. Getting into the data set I've used here was of 1,200 songs, and these were mapped to specific features or personality traits. Like, for example, a song can have like a specific tempo or acousticness and danceability and all of those things that basically define a song and could define why does a person like this specific song, so we can think of a pattern forming using many different songs. And another thing about this data set is that it actually has labels that indicate whether in the past the user has liked a specific song or if they haven't liked that song. So moving on to pre-processing, here we used PCA. And the reason why I've gone with this is because you're trying to reduce dimensionality of the data set, as in what that means is that there's a lot of features for each individual song, but we're not going to consider every individual feature because that would be quite impractical. So we only want to keep the ones that are important and that are useful for us while we discard the rest. So that is what we do in the pre-processing to make it easier for the algorithm to handle and to fit it within a specific range as well. Moving on to the quantum machine learning algorithm, what I've used over here is a hybrid approach.
Roshani,
Yes.
uh, we lost your screen sharing.
Oh, did you? Okay, just give me a second. Let me reattempt. Okay, I'm hoping you can see it now, right?
Yes, we can. Yes, we can see it.
Okay, great. Yes, so where was I? The algorithm. So what I've used over here is a hybrid approach, meaning I've used quantum circuits within a neural network framework. So what this involves is quantum circuits where each data sample is encoded into a quantum circuits, and we're using PQCs or parameterized quantum circuits because these circuits they have trainable parameters and that can be optimized as you're training your model. And for the quantum layers, because I mentioned that you're using quantum circuits within the neural network, for that I've used TensorFlow Quantum, where the quantum circuits are integrated into TensorFlow Keras model. And then this allows the quantum circuits to be used as layers within a neural network. Now, before I continue, I just want you to look at this diagram over here so you have a little bit of an idea of what I'm trying to do. So you have different sessions of what a user has, how they've listened to music. And then you're like, say for example, in one session they've listened to 20 tracks. Each individual track has its own acoustic features, and acoustic features as in what I had previously said, like the tempo, or the emotion that it represents, and the user behavior, as in has the user liked the song in the past or have they not liked the song. We're going to be considering these for training and then for testing as well. Now, just to go over the entire process from beginning to end once, what we do, we start with quantum circuit encoding, where each song's feature is converted into a quantum circuit, and each feature controls the rotation of a qubit. After that, you're going to train the quantum model, where these encoded feature circuits are fed into the PQC, which is within our integrated within the neural network. And then after the model trains using this labeled data, it'll have the ability to actually differentiate between the songs which are a good recommendation and those which are not a good recommendation. We then go into the prediction process, where here what happens is that the trained model will predict a recommendation score for each individual song based on its learned parameters. I'm gonna get more in depth into that. But then the last process is recommendation itself, where these scores that we predicted in the third process, these will undergo an analysis, and the songs that have a high positive score will be a strong recommendation, and the ones that have a negative score will be, well, not a great recommendation. This is going to be taken into consideration using the user's past preferences and their listening history. That's the reason why, the more music a user listens to, the better idea we get of what kind of music we can recommend to them, because you have a lot more data to work with. And so to conclude, what actually happens in the prediction process is that you're giving a specific score to every individual song. And this score can be anywhere between -1 to 1, where 1 would indicate that it's a really good recommendation, and -1 would recommend that it's a pretty bad recommendation, and anywhere in between. So because we don't actually want to consider all of these scores, what we do is we set a threshold, right? So we say that, okay, we're only going to consider songs which have a score above zero point 0.8, because anything below the score is, it's just not a good recommendation. You wouldn't want to recommend that to a user, because then the user's never going to use your platform again. So we set a threshold for that, and that is how you recommend music to a user. And before I finish, once again, if you have not already scanned this QR code up here, please do, because if you have any queries about the project, or if you want to look at the code or look over the description and the intricacies of how everything's been done, it's right here. So that's it for my entire presentation. Thank you so much for listening.
Roshni, did you have any results and any comparison with classical recommendation systems versus quantum-based recommendation systems?
Yes, actually, everything is given right there on the QR code itself. So I just think, because we're quite short on time here, so I thought that if there's anything that you want to look into, like the results itself, then it's all given over there, so it can, you can look at it at your own time and comfort.
So, can you summarize the results?
It performed quite well. I would actually say that so far the QML model didn't necessarily perform exceptionally better than a classical model, but it was there, and I think with a bit more time and a bit more work, it can be made better. That was really it in like a summarized way.
Okay, thank you. This is a very interesting application of quantum ML. Uh, so thanks for the presentation.
Yeah, thank you so
Uh,
much.